Good morning to everyone. I'm Dr. Sumi MS. The name of the course is Electromagnetic Fields and today's lecture topic is Normal Incidence onto a Dielectric. On completion, the students will be able to understand the characteristics of a dielectric and obtain the wave incidence on a lossless dielectric and lossy dielectric. Lossless dielectric. We replace the perfect conductor which we saw previously with a lossless dielectric medium of permittivity epsilon 2 and permeability mu 2 with a uniform plane wave which is incident normally from another medium with permittivity epsilon 1 and permeability mu 1. In addition to the incident and reflected fields for Z less than 0, there is another transmitted field which is that the obtained as the wave is partially reflected and partially transmitted. So the incident wave is partially reflected across the negative Z direction and is partially transmitted across the positive Z direction. So equations 1 and 2 represents the electric and magnetic fields for the incident wave, and equation 3 and 4 represents the electric and magnetic fields for the reflected wave component, and equation 5 represents the electric and magnetic field for transmitted wave component. It is necessary that to use the appropriate wave number as well as intrinsic impedance for the respective region, and there is no wave traveling in the negative Z direction in the second region, as we consider there are no boundaries across Z greater than 0. So let us this diagram represents a dielectric being separating two mediums, and a uniform plane wave is normally incident upon the dielectric boundary, and a part of the wave is reflected and part of the power is being transmitted. The unknown quantities of the reflected and incident electric fields can be obtained from the boundary conditions of continuity of tangential E and H fields, and the relation between the reflection and transmission coefficient is obtained as 1 plus R is equal to T, where R is the reflection coefficient which is given as the ratio of reflected electric field to incident electric field component, and T is given as transmitted electric field to incident electric field component. And if both the mediums have the same wave impedance, that is eta 1 is equal to eta 2, then there is no reflected wave. Time average power flow. The time average power flow is obtained by the given expression, in which the second part of the expression is related to 0 as it has only imaginary part and there is no real component present in it. So the being purely imaginary, the real part is 0, and hence the time average power flow just equals to the difference in the power flow in the incident as well as reflected waves. This can also be equated to the transmitted power. Lossy dielectric. If medium 2 is considered to be as a lossy dielectric with ohmic conductivity sigma, the above equations can be used by replacing the permittivity with a complex permittivity epsilon 2 cap, where epsilon 2 cap is given as epsilon 2 times 1 plus sigma by j omega epsilon 2, where sigma is the ohmic conductivity and omega is the angular velocity, so that the wave impedance in this region is obtained to be as complex, and the intrinsic wave impedance eta 2 is equal to root of mu 2 by epsilon 2 cap. The losses in this medium is considered as low loss as well as large loss. Low losses. If the ohmic conductivity is small, we can neglect it in all terms other than in the case of wave number, that is wave number is related to the angular velocity as well as the conductivity and the relative and the permittivity and permeability of the lossy medium. And large losses. For large losses conductivity, for large conductivities, the displacement current is negligible in the medium 2, and the wave number and impedance in this lossy medium are complex. So here the wave number and the intrinsic impedance are observed to be as complex terms, which has both real and imaginary part. The fields decay within a characteristic distance which is equal to a term called skin depth, which is given as del is equal to square root of 2 by omega mu to sigma. This is why communications to submerged submarines are difficult. For seawater, mu2 is equal to mu naught, that is the permeability of the medium is equal to the relative permeability, which is equal to 4 pi into 10 to the power minus 7 Henry per meter, and the conductivity is 4 Siemens per meter, so that for a 1 megahertz signal the skin depth is observed to be as 0.25 meter, whereas replacing the signal with velocity and at 100 megahertz and 100 hertz, the skin depth obtained can be increased to 25 meters. If a submarine is within this distance from the surface, it can receive the signals properly. However, it is difficult to transmit low frequency signals because of large free space wavelength, that is lambda is increased to 3 into 10 to the power 6 meter, and also the conductivity approaches infinity. So that now in this case the field solution approaches to the case of a wave being incident upon a perfect conductor. Quiz questions on normal incidence onto a dielectric. Determine the wave incidence on a lossless dielectric. Determine the wave incidence on a lossy dielectric. Thank you.